Hello, everyone. Welcome to the pre-recorded lecture for 20th November for Solid Geophysics. And as promised, we are going to start discussing today about geothermics, a new chapter, geothermics. So it's all about the heat system, all about the heat system of the Earth, and of course, its application. Application. Okay. So we will first understand some fundamentals. Okay. So where we would look essentially around what is the actual source of the heat, okay, in the earth. Source, we will see their distribution and of course gradient, and what are they responsible for? I mean, what do they control? Okay, what does it control? And then, of course, the application of the heat system of the Earth, we are mostly going to look at the geothermal energy. Okay? So, geothermal energy is one of the renewable, clean type of energy. Okay? So, and it's gaining more and more importance in recent times. Okay? So, in the first part, we will look at the some of the fundamentals around the heat system, and then we are going to look at its application. Okay? So let's begin with the with some fundamentals. So before we get into the heat system, let us understand how the physics between the mechanical forces and the forces that arise due to heat, or the whole physics of heat, how do they compare with each other? Okay, so gravity is an application of fundamental force of law, one of the four fundamental forces, as we have discussed before. Gravitational attractive force between masses cause motion, and that is determined by three laws of motion, which we call as Newtonian mechanics. Of course, you know about these three laws. And then we introduced you to the concept of isostacy. That concept uses the concept that of an ideal fluid in a gravitational field that produce the force called weight. This leads to the concept of stress. We have discussed about stress and pressure as well, and this leads to the concept of buoyancy force as well. Buoyancy force as well, right? We talked about gravity. We talked about isostasy in details. Now, heat and temperature is a very different physics that applies Newtonian mechanics to system with 10 to the power 24 molecules. Okay, so here we are not, here still we are discussing about continuum mechanics only, but the number of molecules, they are discrete, they're small, and they are distributed, right? So if you think about the example of a gas. Now, if we want to understand their mechanics, then we have to actually, study each and every particle individually. But that is not feasible. That you and you understand that from a common sense, from your common sense. So happily, we have discovered that thermal and chemical equilibrium and thermodynamic averages of many particle system is well defined. So the microscopic averages like temperature, heat content are defined by simple equations. Okay, so that works as an advantage to us. Now, this is a beautiful slide which I really like. What actually shows that how energy, heat, temperature, and work actually are kind of intertangled and correlated with each other. If I take you through this nice workflow, you will kind of understand what we are trying to achieve here. So, energy can be divided into two parts: potential energy and kinetic energy. So potential energy, which is the major component of chemical energy, is stored in chemical bonds and released or absorbed in chemical reactions. I don't have to emphasize what it exactly means because you all know about it. You have studied chemistry from high school. Now, there is another part of energy that is what we call as kinetic energy, which is the major component of thermal energy and consists of random molecular motions. Okay, so the molecular motions essentially provides the kinetic energy, which is expressed as thermal energy. Right now, energy is conserved. We all know about it, but of course, energy is transferred. How it is transferred? By the process of either heat transfer or by the process of work. Now, heat is only partially convertible to work. So, for example, if you want to use the heat energy to do some work, you can only partially convert that. But work can be completely converted into heat. You know about this. Yeah, I'm sure you have read about this in your high school physics. Heat is defined as transfer due to a difference in temperature. You know about it as well. Because if there are two things, there are two bodies which of different temperature A and B, and if you put a connection through them, heat will flow from higher temperature to the lower temperature. It doesn't exactly depend on what is the total amount of heat in these bodies. It actually depends on their temperature difference, right? Now, heat relates to temperature with something called heat capacity. Now, temperature is expressed in arbitrary scales. Most commonly used scales are Celsius, Kelvin is the absolute scale, and Fahrenheit generally used in the USA. And defined by 0 point, we know what zero is, and magnitude of degree, right? So 0 degree Celsius we know, and then 1 degree, 2 degrees, 3 degrees Celsius or Kelvin. We all know about that. The temperature is measured by observable effect on physical property of a substance. For example, in a thermometer, we see the expansion of mercury, right? We see how the mercury length, essentially, mercury column length is actually increasing due to the expansion of the mercury when it is put in an elevated temperature, right? So the observable effect on a physical property, in this case, expansion of mercury, is essentially is a measure of the temperature. Now, energy is measured by its effect on matter that loses or gains or possesses it, and is expressed on a scale whose 0 point is arbitrarily set, with consequences that only changes in energy can be observed. Okay, so now this kind of puts everything together into perspective. Now let's look at the first law of thermodynamics. I hope you have read about it, but let's no harm in refreshing once more. When two objects are separately in thermodynamic equilibrium, it's a third object, then they are in equilibrium with each other. Okay? So what does that mean? That means suppose I have object 2 and object 3, and I see my object 2 is in thermodynamic equilibrium with object 1, which is my thermometer, and object 3 is also in thermodynamic equilibrium with object 1. What do I mean by thermodynamic equilibrium? That means they have the same temperature and hence there is no heat flow occurring in between them. Okay? So the first law of thermodynamics says that if object 2 is in thermodynamic equilibrium with object 1 and object 3 is also this is the zeroth law of thermodynamic equilibrium, zeroth law of thermodynamics, as they say. Okay. And object 1 is also with in equilibrium with object 3, then object 2 and object 3 has to be also be in equilibrium with each other. Now, next is the first law of thermodynamics. The first law of thermodynamics is the application of the conservation of energy principle to heat and thermodynamic processes. So the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. Okay. So delta U is the change in internal energy that can be is equals to the heat added to the system and the work done by the system. Okay. So this is your first law of thermodynamics. My apologies. This one is called the zeroth law of thermodynamics. Okay. Now, so we talked about external energy and internal energy. So internal energy involves the energy in the microscopic scale. For an ideal monoatomic gas, this is just the translational kinetic energy of the linear motion of the hard sphere type atoms. Okay? And the behavior of the system is well described by kinetic theory. However, for polyatomic gases, there is rotational, vibrational kinetic energy as well. So, for a monoatomic gas, as they are saying, it's only the translation energy that matters. But for polyatomic gas, we have rotational as well as vibrational energy also in them. Okay? That constitutes the internal energy. Then in liquid and solids, there are potential energy associated with the intermolecular attractive forces, which is not present in gas, of course. A simplified visualization of the contributions to the internal energy can be helpful in understanding the phase transition and other phenomena which involves internal energy. So this is only translational kinetic energy, that is for monoatomic gas, vibrational rotational kinetic energy, that is for polyatomic gas, okay, together with translational kinetic energy. And then if it is a solid or liquid, it will have an added potential energy as well, potential energy for intermolecular forces, okay. So now if we try to see what is the relationship between work and heat, so the amount of mechanical work done can be determined by the equation derived from Newtonian mechanics. This is a very fundamental equation, you all know. Work is equals to force into distance moved in the force direction. It can also be described as the product of the applied pressure and displaced volume. Okay, so you know about the example of a piston. So if there is a piston and you are applying pressure, the work is exactly equal to the applied pressure, the amount of pressure that you are applying. A pressure means force per unit area multiplied by the displaced volume, the volume it is displacing, right? Or the other way around, you are pulling the piston. In that case, you are expanding the volume, and here you are providing actually tensional stresses, right? The unit of work is in joule or J, which is defined as the amount of work done when 1 Newton acts for a distance of 1 meter in the direction of force. So 1 joule, 1 Newton meter. Solid Earth, liquid oceans, and gaseous atmospheres are all heat engines that do work on the planet and create kinetic energy due to the disequilibrium associated with lateral variation in temperature. Okay. So anything that we are studying, the solid earth, the liquid ocean, or the gaseous atmosphere, they all behave as heat engines. So what happens? There is a change in temperature. There is a change in temperature that would create a disequilibrium, and that disequilibrium will be actually manifested by the work done by the system. Okay. So if we try to look at the solid earth, of course, it has a hot bottom and a cold top. Crust is colder than mantle and core. So there is a convection cycle that moves to heat the cool solid planet, right? That's why there is a convection cycle set up, right? And then there is, of course, the conduction within the crust as well. Okay, convection in the mantle and conduction in the crust. In the liquid ocean, hot at equator Y and cold at poles. Hot at equator, simply you know why. Poleward flow moves, so that's why we see the ocean currents, right? So the hot water from the equator actually moves towards the ocean, and the equilibrium is maintained. Hence, we see, even if the water freezes in the polar region, there are still some gullies which are even very much below zero. A lot. I mean, maybe a third, minus 30, minus 35 degrees centigrade as well. You have liquid water because of the ocean current transport. Then gaseous temperature, gaseous atmosphere, hot at equator, cold at poles, poleward flow moves heat. Okay. So mechanical equivalent of heat. Heat flow and work are both ways of transferring energy. As illustrated in the heat and work example, the temperature of a gas can be raised either by heating it or by doing work on it, or a combination of the two. If I want to elevate the temperature of a gas, I can do some work on it. That work will be converted into heat energy, and will rise its temperature. Or it can also, I can simply elevate the temperature by putting a heat source around it. Okay. So in this classic experiment of 1843, James Joule showed that the energy equivalence of heating and doing work by using the change in potential energy of falling masses to steer an insulated container of water with paddles. Careful measurement showed that the increase in temperature of the water will be proportional to the mechanical energy used to steer the water. Okay, so this is a very famous example. So I have a liquid, for example, maybe this is water, and then there is like a wheel which I can rotate at any speed by putting some weight in this pulley which is associated with this wheel. Now I can measure the work done by measuring the weight, of course, and then I can see, while I doing the work, what would happen. This particular wheel will rotate, and it will elevate the temperature of the water, and we can measure the temperature increase of the water, and then we can uh, plot the work done and the temperature increase, and we will see that they are proportional. Okay. Now this is what we have been talking about. Say, for example, I have I have a piston which is filled with gas, and I am pushing that piston with a force F. And after we are going with a distance d. Okay, so this is my initial state, and after traveling of the piston with a distance d, I see that the temperature has raised from 100 degrees centigrade to 200 degrees centigrade. So work done is equals to F multiplied by d. F by A is essentially nothing but the pressure. A multiplied by D is volume. So P delta V, the force can be also described as P delta V. Now I have increased the temperature as a result of doing the work P delta V from 100 degrees centigrade to 200 degrees centigrade. Now I can also achieve 200 degrees centigrade temperature of the gas by just putting a Bunsen burner under it, right? And the temperature can be heated up to 200 degrees centigrade. Now, if I find the final state at any of our observation and see that there is a volume of gas with an elevated temperature from the surrounding, which is we will not be able to say for sure whether it has been elevated by the temperature by the work done or just by applying heat. That is impossible to say, or it could be a combination of both. Okay. Now, of course, you know about adiabatic flow and adiabatic system and isothermal system. I don't have to. I'm not repeating them. If you don't remember them, please go ahead and refresh yourself. What do they mean? Yeah, isothermal means the temperature remains constant. In adiabatic system, temperature is not constant. You can read about them from your high school physics book. Now, as I said, that the everything in here is a heat engine. Here I can see the rainfall cycle, of course. So you know how rainfall happens. There is the energy of the sun, which actually vaporizes water from the water bodies on the earth. That essentially forms cloud, and then again it forms the rainfall starts, right? And everything is due to the disequilibrium created by heat. Of course, the wind actually flows due to disequilibrium of heat, and we can use that wind energy, of course, um, to create um, electricity. Okay, and this is, you can see how the temperature profile across latitudes. Okay, so you can see the equator is pretty hot, and the temperature slowly decreases as we move towards the pole. And of course, that creates an disequilibrium, and that disequilibrium is responsible for the ocean current as well as the wind that flows from the equator to the pole, and from pole back to the equator. Okay, the hot wind goes towards pole, and the cold wind comes back to the equator, and that cycle is actually maintained. Hang on for a moment. My apologies. It's an urgent call, so I had to take it. Let's continue then. Okay. So of course, the heat engines are there in the we have created a lot of heat engines for our own purposes. You can see steam engine is one of the examples by which the trains used to run previously, where the heat used to be converted into work, and that could run a train. Okay, the locomotive. So um, the coal-fired power station, the example is shown here. Is the turbine. Of course, what is done? The coal is burned, and the heat energy, is actually transferred into a mechanical energy, of course, and that mechanical energy forms the electricity. Okay. Of course, in car engine, we see the same thing. Now, let us look at something called Newton's cooling law. Newton's cooling law says dq dt is equals to H multiplied by A into temperature of the environment minus a temperature of the object. Okay, so that means, and Q is the thermal energy. So the rate of change of the thermal energy with time is equals to H, which is the heat transfer coefficient, multiplied by area of the heat being transferred, multiplied by the difference in the temperature between the environment and the temperature of the object. So, for example, I am keeping a hot object in a colder environment, and I am allowing that object to cool to dissipate its heat in the environment. Okay, so that follows Newton's law. So, the rate of cooling of that particular object is actually directly proportional to the area of the heat being transferred. So the is the surface area of the object itself, yeah, which is in contact with the environment, and then it's also directly proportional to the temperature difference between that object and the um, and the area, and then it's multiplied by and then there should be a constant, and that constant is called heat transfer coefficient. Of course, that depends on the medium itself. Okay, not important. Okay, now this is another important equation to remember. So what does the heat flow uh, equation conserve? It conserves heat energy. The change in the internal energy of material within a volume during delta theta means the change in temperature, okay, is equals to delta theta is change in temperature. Okay, so change in the internal energy of a material within volume during the change in temperature delta theta is equals to heat conducted into the volume during the same temperature change minus the heat conducted out during the temperature change plus the heat generated during the temperature change. So it is the summation of all these three, okay, which is expressed by this mathematical term, of course. Now, if we think about the heat flow equation and understand that with a simple analogy, say for example, I have two material, which one is cold and other is hot, and then this is the like the passage or the medium through which the temperature can actually transfer from the hot object to the colder object. Okay, and then so if this intermediate, the transition area, which is twice the thickness, the heat flow will be half the area, heat flow will be half. The different material will have different heat flow. Okay, that will depend on the coefficient of heat transfer. Okay, and double the temperature difference, double the heat flow. Okay, that essentially is Newton's cooling law. It's the same thing that we are seeing here. Okay, of course, heat essentially also initiates diffusion in gas molecules, but we are not too much interested in that. But let's see. Then the heat transfer requires delta T is not equals to zero. That means it has to be in this equilibrium, and heat transfer actually takes place by four processes. Heat transfer takes place by four processes. We know about them. Conduction. Conduction is the diffusion of atomic vibration at the atomic scale when there is a thermal gradient. Conduction can never be stopped except by putting a perfect insulator in between. Okay, and conduction typically happens in solid. Then convection. Convection is the movement of heat by material flow. Here in conduction, it is just the atoms actually vibrate. Yeah. In case of convection, the material does itself flow. Uh, Convection happens when the thermal variations creates buoyancy forces sufficient to overcome the viscous strength of any fluid. And as we know that the convection cycle happens in the mantle, so in our for our particular case it is the mantle rock. The earth is very viscous fluid that flows at the rate of 10 centimeter per year as manifested by plate velocities. Okay. Radiation is the movement of the heat as infrared electromagnetic waves and hence can propagate through free space and transparent substances, right? Now, these are the three processes by which heat gets transferred. Now, alpha and beta decay, beta radioactive decay, is called radiation, but is not electromagnetic wave. Okay, so remember that this is the electromagnetic wave propagation we are talking about. We are not talking about the radioactive decay, such radiation. Okay, they're confusing, but they are not exactly the same thing. Okay, not important. You know about it. So now in the study of transport phenomena, flux is defined. Flux is another important thing to understand in heat flow. Flux is defined as the amount of heat flows through an unit area per time. Yeah. So hence flux is a vector, and we are here mostly interested in the heat flux. Heat flux is the rate of heat flow across an unit area in a per unit time. Okay, so heat flux is the rate of heat flow across the unit area per unit time. Okay, now flux is proportional to the density of the flow. Flux varies how boundary faces to the direction of the flow. As you can see, if it is perpendicular, there are more lines passing through. Okay, density of the flow, if whether more heat is actually being propagated or less heat being propagated, and flux is proportional to the area of the boundary. Smaller area, less heat can flow actually. Now, from the boreholes which are drilled inside the earth, people have calculated geothermal gradients, and you can see there are different geothermal gradients that people have proposed. Okay, so that varies from around 83 point, so around 84 degrees centigrade per kilometer. This is around 72 degrees centigrade per kilometer. This is around 62 degrees centigrade per kilometer. Okay, and this is 134 degrees centigrade per kilometer. So the moral of the story that the borehole, the geothermal gradient varies a lot depending on um, where exactly we are. In few cases, we have very thin crust, maybe near to a volcano. In those places, we will see, or very close to the mid-oceanic ridge, we will see a very steep geothermal gradient simply because the temperature will increase very quickly with depth. But in case where the crust is fairly thick, in those places, the geothermal gradient will be little bit gentler. Okay. So this is the heat flux as is shown in the United States, and you can see that the heat flux varies um, at different places, right? I mean, it's not constant everywhere. So the temperature at 3 kilometer depth, we can see also varies spatially. So what are the things that happens due to this heat flow? So we see uh, hydrothermal fields. We see hot springs coming up. Oil and gas maturation takes place. The organic matter cooks to oil and to form oil and gas. Volcanoes happens, earthquakes happens, hydrothermal mineralization happens, plate tectonics happens, geothermal power production happens. We will talk about it in detail. Mid-oceanic ridges through which the volcanic material comes up and forms the crust happens because of the temperature differences. subducting slabs in the trench or the you know converging boundaries. That is where happens. A metamorphism of the rocks also happens due to temperature. Now, how plate tectonics is actually related due to this thermal disequilibrium? That is something we will try to understand. So the Earth is hot at the core mantle boundary. It's around 4,000 degrees centigrade. And it is cold at the surface, only 19 degrees centigrade, and very cold at space, around 270, minus 270 degrees centigrade. So this large temperature contrast means that the Earth is in thermal disequilibrium and must be transferring heat into space. The internal Earth is cooled by convection that delivers heat at the base of the lithosphere, where the heat is then conducted in the lithosphere because lithosphere is solid, and then the heat flux warms the temperature, and finally the atmosphere always radiating heat into space. So in the in the mantle, the major phenomena by which heat actually gets transferred, that is by convection. In the crust, it is done by conduction, and then in the atmosphere, it is done by radiation. Excuse me. Note, the Earth primarily cools itself by creating new lithosphere. So the new lithosphere is being created um, at the mid-oceanic ridge. Why does the Earth do that? Simply because it wants to cool itself. Okay, because it wants to decrease that disequilibrium. Okay, anything in disequilibrium wants to come into the equilibrium. That means it wants to bring all the temperature back to the same. Okay, and hence it has to cool down. Hence it creates more crusts, and hence the plate tectonics is actually started. At ridges that is pulled across the ocean basin and finally subducted deep into the mantle to cool it. Okay? Because the when the cool slab actually goes into the mantle, then again you are actually like putting colder stuff into the mantle, and the mantle is also constantly losing temperature. So the solid earth is a heat engine because the work done moving the plates and raising the mountains and pulling apart the ridges and rifts. Okay, because of that thermal disequilibrium, we see all these plate motions happening. As a result, we have ocean building, we have mountain building, all these processes happening. So it's a heat engine where that thermal disequilibrium is creating all these processes. Okay, so ocean atmosphere is also similarly our heat engines. So in the last 4 billion years, the Earth's cooling has been around 100 degrees centigrade per billion years. So the Earth is predicted to reach thermal equilibrium with space in 10 next 10 billion years. Okay, so that's the end of the story of the Earth when it will. I mean, at least all the plate tectonics, all the moving things will stop as it comes to the equilibrium with the space, and it will happen after 10 billion years. Okay. Till then, this equilibrium will be maintained unless something else happens, and it will keep on continuing doing this um, beautiful cycle. Now we talked about conduction, convection, and radiation, and what does it heat. Okay. Now I will just finish that the fundamentals on geothermics by introducing you to two types of geothermal gradient. One we call as the isothermal geothermal gradient, and the other one we call as the adiabatic geothermal gradient. Okay, so what we see, the temperature with respect to depth in the lithosphere is not a straight line, which is called the conductive geotherm. Okay, so this is called the conductive geotherm, which is around 30 degrees centigrade per kilometer, which is the normal geothermal gradient. The ones that we have been seeing in that example from boreholes, they are actually really steeper geothermal gradients. That means they represent you know shallower heat sources. So generally it's around 30 degrees centigrade per kilometer, and in the crust it is gentler, which we call as the conductive geothermal gradient. But in the mantle it is actually very steep. It's around zero point 0.3 to zero point 0.5 degrees centigrade per kilometer, and this is what we call as the adiabatic geothermal gradient, or simply adiabet. This temperature rise with depth is because each parcel of heat is compressed into smaller volume due to the pressure increase with depth. So it cannot vary as gently as it happens in the crust. It's like smaller packets of heats. Okay? And then that has a fairly steep geothermal gradient. Okay, so remember, before above Moho and below Moho, you have to use different geothermal gradients to calculate the temperature. Okay? So I will stop this particular fundamental part in here, and next we will talk about in the next video we will talk about the use of the heat source of the earth and how we can use it for geothermal energy. Thank you.